Hello and welcome back to lesson 30, diffraction and interference. Now earlier on in lesson 23, I believe, we talked about the theories that supported the wave model of EMR. We're just going to look at the math and more specifics around those theories. As a result, we're going to look at three specific concepts: the Huygens principle, Young's double slit experiment, and diffraction gradients. All of which we've kind of talked and seen before. The first concept is Huygens principle, which is the idea that EMR travels like a wave. The first piece of evidence that suggested this was the single slit experiment. If we pan down here, of course, we see how Huygens tried to prove this. He kind of referred to light as traveling in wavelets, and that they would travel together, overlapping, resulting in a consistent or uniform beam of light. If there was an opening small enough, it would make these wavelets difficult to travel through, causing breaks or gaps in the wavefronts. Looking at this applet as we did before, we can see that as you mess with the size and width of the slit, we eventually get diffraction occurring, regardless of the color, but obviously because of the difference in the wavelength, which is the size of the wave and the size of the opening or the slit, we see that the two result in different diffraction patterns. The key thing to note, of course, is that they're relatively close together. We're talking, in this case, 577 nanometers and 2700 nanometers, like in the same ballpark. This really only works if the opening is very small, similar in size as the wavelength. If we actually were to use, like, say, for example, a large wavelength and a very small opening, we notice that there really is no diffraction. Now, because Huygens had problems explaining this and could not really mathematically deduce or provide evidence why it worked, it required the work of Young's experiment, the double slit experiment, before this mathematical explanation could be proven. Now, his experiment is pretty straightforward. If we pan down here, we see that if light traveled as particles, bam, it would hit the first screen, and then only particles traveling in a straight line would make it through, hitting the second viewing screen. In Young's experiment, he figured that if light was traveling as a wave, it would hit the two openings, making those wave fronts or wavelets that was expected, and there would be some kind of interaction of those two waves. That interaction or interference can be seen in this applet here. You can see these 2 point sources producing waves, producing kind of a black and a gray line. Now, anywhere where those two lines interact or touch is going to be some kind of interference. If I just pause it here and go over to the applet, we can see that wherever 2 gray lines meet or 2 black lines meet, we have a red line. And that is repeated here and here and here. These are going to be points of constructive interference, hence the red and the red. This would mean that anywhere that a black and a gray line meet, we got points of destructive interference, which really means they cancel each other out. So what we have is points of superpositioning or waves magnifying in themselves, and points of deconstructive interference where waves cancel each other out. That would mean we'd see, for example, bright spots and dark spots. And this is exactly what we see. On the Young's double slit experiment, as we increase the distance between the openings or the slits, we see those diffraction lines appearing, which represent merely lines or points of interference, both constructive and destructive. Now, the key thing that was different with Young's experiment was that, unlike Huygens, Young was able to put a mathematical relationship to it. We see here his formula, lambda is equal to xd over nl, and the variables, of course, all being there on the side: wavelength, distance from the central fringe or the middle point, distance between the slits, which is the gap, and the order of the fringe, meaning simply is it the first, second, or third bright spot. And lastly, the distance from when the light is broken up through the slit to the actual screen. The key thing here is that Young could actually mathematically explain the diffraction pattern with this formula, providing mathematical evidence supporting this theory. This is critical because without the strong mathematical support, it's very difficult for a theory to hold true. Now, below here in the notes are just some examples of going through how to do this. We'll do some examples later in class. But it's worth mentioning that there's a second formula based on trigonometry and the angle between it. There should be a relationship between, of course, where those bright spots are and the angle, of course, because they occur at even increments. So the other formula is lambda is equal to d sine theta over n, and theta is simply the angle between the first bright spot, which is n0, and whatever one you're going to go to, n2 or n3 or whatever. Lastly is diffraction gradients. Now, it's pretty difficult to make just 2 small openings. So normally what happens is they make a bunch of scratches on like a sheet of glass or a sheet of plastic. That gives you this multiple line kind of appearance, like blinds or whatever. This is what we typically use in class because it's simply easy to find and cheap and affordable. Now, the one problem with this is that diffraction gradients aren't given to you in the distance between 2 openings, but rather the number of scratches or lines on the actual screen. So this is usually given to you as a value like in example 3 here, where it's like 600 lines per millimeter. That means you have to do a quick calculation to figure out the gap between the two lines. All you do is you take 1 and divide it by 600, or the number of lines per millimeter. This reverses it, of course, and gives you the distance between two lines. Other than that, at this point, it's just really working with those two equations. So work on the practice sheets that I've given you and the concept checks, and we'll see you back for lesson 31.